Welcome, students. Uh, this is a makeup class since in the last class we had a issue with the alarm and we had to leave early, right? So let me recall few definitions we had. So the first definition was definition of sets. So a set is a collection of objects. It's a collection of objects. And there are a few sets we already know. For example, set of natural numbers, as we discussed last time. So set of natural numbers. For example, is given by n. This is the notation for it. And it consists of 1, 2, 3, and so on and so forth. Similarly, we have set of whole numbers. Represented by W. And this is essentially natural numbers along with one extra element, 0. Okay, so set is a way to combine objects which we are interested in, right? Say, for example, set of students in this class in, right? So then in that case, I will list all the students' name, right? And this would be a finite set, right? Because the size is finite. And this set is of size infinite, right? So it's an infinite size set. Okay. Now, recall, we wanted to talk about how do we make a set of natural numbers. So we wanted to talk about building blocks of natural numbers. So before that, make the following observation. A product, if you multiply, product means to multiply. So product, to take product is to multiply. So a product of two natural number is a natural number. Okay. So for example, if I take, let's take two natural numbers, say now 5 times 21. Yeah, when you multiply, you will see this is 105, and it's also a natural number. Similarly, take any natural number of your choice, say 2 times 1, also a natural number. So when you multiply natural numbers, you get natural numbers, okay? So when you have a representation like this, so another example could be, say, 6 times 10 equals to 60. So in this case, if we look at this, let's develop some more vocabulary. We say so 60 is a multiple of 6, and 60 is also a multiple of 10. From here we can read that, and we will say following as well, that 6 and 10 are factors of 60. Okay, so again, we are trying to develop some vocabulary so that we can do mathematics easily. So if I want to abstract this in terms of symbol, right, we discussed that symbolism is important. It helps us to make more general statement. So if I have A multiplied by B equals to C, so in this multiplication statement or product statement, what do we have? We have that these are factors and this is a multiple. To be precise, A and B are factors of C, right? I mean, A times something is C, right? B times something, that something is a natural number, is C. So A and B are factors of C, and C is multiple of A and also B, right? So this is again some language. Now, our goal is to mini goal rather, look for factors. So here A is a factor of, so let's read this statement again. A is a factor of C. What does it mean? It means there is some B natural number such that A times B is C, right? So we can write the definition now. So a non-zero whole number, or you can say non-zero natural number, because non-zero whole number is a natural number, right? That is a natural number. A is a factor of whole number M. So this guy is a factor of whole number M if what happens, we have A multiplied by something gives me M, isn't it? Similarly, I mean, let's go back and check it out, right? So 6 is a factor of 60. That means there is some whole number. Let's call it 10. Well, actually, we don't need to call it 10. It is 10, such that 6 times 10 is 60. So similarly, a whole number, so let's repeat, a non-zero whole number A is a factor of whole number M if there is a whole number B such that what happens, such that A times B equals to M. So this is the definition of factor. Okay, so let's see some examples. So if I take 30, so what are the factors of the 10 is a factor of 30. Also, there are more factors, right? 1 is a factor of 30, right? Why is that? Because 1 times some number, whole number is 30. What is that whole number? 30. Similarly here, 10 is a factor of 30. Why? Because 10 times some whole number is equal to 30. What is that whole number? 3. Similarly, a 3 is a factor of 30. Why? Since 3 times some whole number is 30. What is that whole number? 10. Similarly, 15 is a factor of 30. Yeah. What is that whole number? 15 times what gives me 30? 15 times 2 is 30. That's why 15 is a factor. Okay. So now, so question, how do I write down all the factors? We write all the factors of 30, right? We want to make sure that we get all the factors of 30. We'll see the usefulness of it later. So So you can also think about that 3 is kind of a building block for 30, right? 3 combined with 10 gave me 30, the combination being the multiplication. Similarly, you can think about 30 also as 3 times 10. So 10 times 3, but 3 is same as 2 times 5. So it's 2, 5, 3 multiplied together gives me 30. So these are the factors of 30. So we want to get all the factors of 30, right, somehow. So let's see. For that, we need a building block. And the building block for multiplication is basically, let's see, what is the building block? So 2, for example, is one of the building blocks of natural numbers because you take 2 square. So you get 2, you get 2 times 2, you get 4, 2 times 2 times 2, you get 8, and so on and so forth. So 2 is one of the building blocks. There are many building blocks. Yeah, it's not a one structure. It requires many different kind of building blocks. And those building blocks are called prime numbers. Okay. So what is a prime number? So note again here. So you can see that 2, power of 2 is building on all the multiples of 2, right? So if I take power of 2, so 2 times 2 gives me 2, 2 times 2 gives me 4, 2 times 2 times 2 gives me 8, and so on. So as you can see, 2 is one of the building blocks. Now we could say that, oh, why didn't you take 4? I could have taken 4 as a part of building block, but 2 already builds 4, right? So we want something smallest as possible as the building block, okay? And what is the property of the smallest? In some sense, what is the smallest? What does it mean here? It means that when I factor 4, I get 2 times 2, whereas when I factor 2, I get 2 times 1. So this is some kind of, in some sense, minimum, right? That it's the smallest building block. So let's define it. So what is a prime number? So a whole number or a natural number, a whole number we will not consider 1 as a building block because 1 is everywhere, right? So 8 is same as 8 times 1. And 1 doesn't build anything really if you think about it. Why? Because 1 times 1 gives me 1. 1 times 1 times 1 again gives me 1. It's not building anything really. Yeah. Whereas 2 is a building block. Similarly, 3 is a building block, right? Because 3 times 3 gives me 9. And not only that, I can combine 2 and 3. It builds what? 6 for me using multiplication. So a whole number. So what is a prime number? So whole number bigger than 1 is called prime number. If it can't be broken further, like 2, right? Or like 5, right? So it cannot be, so whole number bigger than 1 is called prime number if it has only 2 factors. It has exactly 2 factors. Namely itself, and then obvious, which is always there, and 1. Okay, so 1 is a factor of everything, right? But if it has no factor other than 1 in itself, then the number is prime. So you see, there's no smaller number. There are no 2 smaller numbers which multiply to give me this prime number. And that's why it is the smallest building block. Okay, so let's look at some examples. 2, 3, 5, 7, right? 7, there is no factor, you can check. So 9 is not, 11, and so on. So these are prime. Okay. So what shall we call numbers which are not prime, right? We need to give them a name. So we will call them composite. So a number, a whole number, which has more than two factors are composite. So let's look at some examples. For example, let's take 2 and 3, combine them together. So 2 times 3 is 6. So you see, 6 has more than two factors, right? What are these two factors? 2, 3, and 1 itself, 1 as well, right? So anything which has more than two factors is composite. Or in other words, if it has more than one prime factor, then it is composite. Yeah, because one is there all the time. So can we list? Let's see. So exercise again. List all the prime numbers less than 30. Okay, let's start. So 1 is not a prime because the prime has to be bigger than 1. So what are the prime? One option is 2, of course, because 2 has no divisor other than 2 or 1. 3 is also prime because it has no divisor other than 3 or 1. 4 is not a prime because 4 is 2 times 2. It has more divisors, right, other than itself, and 1. So similarly, you can see 5 is prime because divisors of 5 is 5 and 1, right? Those are the only two divisors. There's nothing, no more. Similarly, 7 is like that. 11 is also like that. 13 you can check. So 13, again, the divisors are basically 1 or 13. You'll say, how do I check it? Well, one way to check is basically look at all the numbers less than 13 and see if it divides or is a factor of 13. So 2 is not a factor. 3 is not a factor. You can see 3, no multiplication of 3 gives me 13. 4 is not a factor. You can check that. 5 is not factor. Nothing multiplied by 5 gives me 13. 6 is not a factor. Nothing multiplied by 6 gives me 13. 7 is not a factor because nothing multiplied by 7 gives me 13. 8 is not a prime, so I will not consider that. Next one is 11 is not a factor because 11 times no whole number gives me 13. So let's list all of them. 17, 19, 23, 20, 29, and these are all the primes that are less than 30. So now, question is, then next question could be, how can I write all the prime factors? Okay, so for that, first of all, is it possible to do that? And the answer is yes. There's so-called prime factorization. So writing all the factors, all the prime factors is so-called prime factorization. So it says the following. So what is the statement? It says that every composite number, we take any composite number, can be written as product of prime numbers. In a unique way, of course, unique way except to the order, except the order. What do I mean by order? Like instead of writing, say, for example, say I have 60. So 60 can be written as, if you see 60 is 6 times 10, but 6 is same as 2 times 3. So 2 times 3 times 10, and that is same as 2 times 3 times 10 times 10 is same as 5 times 2, right? So it can be written as product of unique factored. So no matter what factor of 60 you take, you will have two 2s, 1 3 and 1 5. And now you can, the order, even if you change the order, it's going to represent the same number. So this is what the prime factorization means. Yeah, that if you write down the factor of a number, you will get the same factors all the time. And maybe the orders are different. Like instead of 2, 2, you're writing 2 and then 2 later on. Okay, so now question is how to find factor question. How to find factors. Yeah, we'll see that why it is useful. It will be useful, for example, when you want to write fraction in the reduced form. Okay, so how do we write, say, for example, 42? Write down all factors. And by factors, we mean prime factors. So how do you write down the prime factors? Okay, so let's start with 42. And let's break it. So we know 42 is same as 2 times 21. Yeah. Then you see 2 is a prime. So I'm going to circle it like that. Then 21 is not a prime. So I can break it as 3 times 7. And 3 is a prime. This is like a leaf, right? All the bottom ones. So I'm going to write 2 times 3. So 2 times 3 times 7. So 2 times 3 times 7 gives me 42. So this is a prime factorization of 42. Okay, let's take another example. Let's take, say, 60. Again, so you know some factors of 60 right away, right? So you can say, well, 60 is same as 6 times 10. Now 6, is it a prime? No, it can be broken further to 2 times 3. Now these are the primes, right? So I'll write it 2 times 3. Then I have, what is 10? 10 is same as 2 times 5. And since these are primes, I'm going to circle them. So what do I get? My 60 is same as 2 times 3 times 2 times 5. And this can also be written as 2 times 2 times 3 times 5. Okay, so this is a tree diagram. Now note that it could have been the following as well. So you could have said, well, 60 is same as, you could have started with different factors, right? You could have said 60 is same as 2 times 30. You know that. Now 30 is same as 15 times 3. Sorry, 15 times 2, not 15 times 3. Now you check. This is composite? Yes. So you need to break that again. All right. So how do you break it? 3 times 5. Now you take the primes, circle, and you multiply them out. So you get 60 is 2 times 3 times 5 times 2, which is exactly same as this guy, except the order is changed. Okay, so this is the factorization. Now, our other interest lies in the following. We are interested in so-called common factors. The common factors of 2 or more numbers. Let's take an example. So what are factors of 42 and what are factors of 60? So let's write it down. So what are the factors of 42? Now, again, we start with the most basic. So we start with 1. Then the next one, 2 is a factor because 2 times 21, right, is 42. Then 3, is it factor? Yes. When you say add this number, you get 6. So 3 is a factor. So 3 times 14 is 42. So similarly, 6 is a factor. 6 sevens are 42. So I'm writing from higher to lower, right? Sorry, lower to higher. I'm just trying to increase. Then I check 7, yes. 8, no, 8 is not there. 9, no. 10, no, of course, 10 is not a factor. You can see that. 11, no. 12, no. 13, no. 14, yes. And then you can check the next ones is 22 and 42. These are factors of 42. Now let's check what is a factor of 60, or what are the factors of 60. So again 1, again 2, 3, 4 times 15, yes. 5 times 5, 12 are 60, yes. Then what else do we have? We have, okay, I missed 6, so I should list all the factors. So 6 tens are, then I have 10, 12, next one is 15 fours, then 20 times 3 is 60, 30 times 2 is 60, and then we have 60. So now what are the common factors here? As you can see, the common factors are, the common factors are 1, 2, 3 as well, 4, no, 6, 7, no, 14, no, 12, 21, no, 42, no. If you check one list, then automatically you have checked the other list because common factor has to be common to both. So if it is not there in one list, how can it be in the other? You know, it cannot be common because it's missing from one list. So common factors are, so here, so we have common factors. So what are the common factors? So common factors are 1, 2, 3, and 6. So now among these common factors, so they're common in both. Among these common factors, there is a greatest common, right? So what is the greatest among these? So 6 is the greatest, right? So 6 is the greatest, the largest of all the common factors. So greatest common factor, or we'll call this in short as GCF. So 6 is a GCF. Okay. So question, is there a easy way to find GCF, or the greatest common factor? Can we do that in an easy way? Why do we want to do it in an easy way? Well, think about it. If I had to calculate it this way, I had to write down all the factors of 42 here. I had to write down all the factors of 60, and then I had to do matching. It's a lot of work. Is there an easy way to find GCF? Let's check. So what you do is the following. You write down 42 is, let's look at the factorization. What we got factorization of 42 was 2 times 3 times 7. So 2 times 3 times 7. And then what do we have? We have 60 was, what did we get factorization for 60? So 2 times 3 times 5 times 2. So 2 times 3 times 5 times 2. Now for the GCF, please pay attention. For GCF, we will take what is common in both. So 2 is common, 1, 2, not this 2 will not be counted here. So this one will not be counted. So we see 1, so 2, then 3 is common, 7, no, 5, no, and this 2 is already have taken in account. So what is the GCF? So GCF, or greatest common factor, is just multiply what is common and don't repeat if it is not there, right? So GCF is going to be 2 times 3, which is 6. And you can see that this little experiment gives us same result from here as well as from here, right? So GCFs are same. Okay, so let's look at another example. So example, find GCF. Again, you should always read it out as greatest common factor, because that way you will remember what GCF stands for, right? So let me write that down here. Greatest common factor of, let's take a big number, 288 and say 360. Okay, so how do we go about this? So first of all, we need to find step 1, find factorization, find prime factorization, right? So we are going to use this method because otherwise listing all the factors of 288 is going to be a cumbersome job. So find prime factorization of 288 and 360 using factorization tree, right? Using the tree. Using tree, yeah. What was a tree? Tree, this is structure. We are calling it a tree, okay? Just a name. All right, so let's see. Let's start with 288. And how do we do this? So 288. So how do we factorize this? Well, it's a big number. So notice that it's an even number, right? It's a multiple of 2. So I can write it as 2 times what remains now. So if I divide this by 2, I have 144. Now this branch, I will not do anything because it's already prime. Now 144 also is an even number. So I'm going to write it as 2 times, what is it? So half of 144 is going to be 72. Again, 72 is still multiple of 2. So it's going to be 2 times, I'm going to circle things later on. So 2 times half of 72, which is 36. Okay. Again, 36 is a multiple of, is an even number. So 2 times 18. Now let's notice again. So 18 is same as what? 2 times 9. 9 is not a composite number. So 9 is 3 times 3. Okay. So now let's mark all the leaves. So what are the leaves now? 2, 2, 2, 2, 2, 3, 3. So what do we have? We have factorization, prime factorization, not just any factorization. So prime factorization of 288 is going to be, I'll write down all of them separately. So 2 times 2 times 2 times, how many 2s are there? 1, 2, 3, 4, 5. So 5, so 2 times 2 times 2 times 2, 5 of those, and then 3 times 3. So this is a prime factorization of 288. Now let's look at 360. So again, we'll do the same technique. So 360 can be seen as 360. I'm going to write it here. So again, 360 can be thought of as, now you can say, oh, well, it's 10 times. So I can either do 2, 2, 2, 2 like this, or I can also try to be quick by saying, okay, 36 seems to be 10 times 36, right? And 10 is same as 2 times 5. And then these are the primes already. So I'll stop there for that branch. for this branch, I'll say, well, okay, so this is, so I know 3 6s are 18. So I get 3 times 6 is 18, or otherwise you could have followed here, right? Like the loop here. Then we have 6 is same as 3 times 2, okay? And then since these are prime, we can just label these guys. So look at the bottommost leaf of this. So what do we get? We get 360 is 2 times 5 times 3 times 3 times 2. Okay. Now comment, always better to write from smaller prime to bigger. Now we want to see common factors. So we should see, say, what repeats in both of them. And then we will chalk that out, right? Like so. So let's see. So what repeats here? So we can pick any one of the list and then compare it with other. Like say you could take 288 and compare with 360 list, or you can take 360 and compare it with 288. So let's start with 360 because this list is smaller. So 2 is common in both of them. So let me just basically say 2 and 2. Then move along. 5. 5 is not common here, right? Because there's no 5 in 288. So not 5. 3. Let's look at 3. So 3 is here and 3 is also here. So 3 is common in both of them. And then whatever is circled, I will not consider it again. Let's move along now. So 3 here. There's one more 3 here. Is there one more 3 here except for that one? Yes. So 3, 3. Then next one is 2. Is 2, another 2 here repeated? Yes. So any one of these 2 is okay. So 2, 2. So what is the GCF, the greatest common factor of 288 and 360? You basically write down what got circled in one of the list. Doesn't matter whether you take the top one or the bottom one, right? You're seeing what is common in both. So 2 times 3 times 3 times 2. So what do we get? We get 3 times, so 6 times 6, so 6 6 are 36. So this is the greatest common factor of both the sets, both the numbers, okay? So this is the method involving the prime numbers. Okay, now, next thing we want to talk about is section 1.3, which is called multiples. So what is a multiple? Recall from the definition. We can say 6 times 10 is 60. So we say 60 is a multiple of 6, also of 10, right? So question is, now write down, so what are multiples of 10? Let's see. So, well, 10 is a multiple of itself, 10 times 1. 10 times 2 gives me 20, so 20 is a multiple. 10 times 3 gives me 30, 40, then 50, 60, 70, so on. So this set is an infinite set. It can keep on going forever, right? So multiples, there are many, right? Infinitely many multiples of a number. Yeah, okay. So let's do some example again. So we want to talk about multiples. So let's look at example. Write a number that is multiple of 6. Again, what is the example? I mean, what is the solution to this? A number. I'm just writing, say, one number. So the 6 times 2 is a multiple, right? Which is what? 12. So when I say 12 is a multiple. Yeah. Now we want to talk about common multiples of two numbers. So let's look at an example again. Let's take the following. So consider two numbers. Say 14. Let's take smaller numbers. So 6 and 15. So what are the multiples of these numbers? So what are the multiples? Let's write it down. So 6 times 1 is 6. So multiples are, the multiple of 6 are, so 6, 12, 3 6 are 18, then 6 4s are 24, 6 5s are 30, 6 6 are 36, 6 7s are 42, 6 8s are 48, 6 9s are so 6 8s are 48, 6 9s are, what is 6 times 9? 6 times 9 is 60 minus 6, so it's 54, and then we have 60 and so on. Okay, it does not stop. The multiples, you can keep on multiplying and get all the list. Now, what are the multiples of 15? So 15 multiples are 15, 30, 45, 60, 75, 90, so on and so forth. This list also keeps on going forever. Now, question, do these numbers, what numbers am I talking about? 6 and 15 have common multiples. So do they have common multiples? That means something which is multiple of 6 and multiple of 15 both. That is what it means by common multiples. So let's check. 6, no. So let's transfers in one list. It doesn't matter which list you transfers through. Let's transfer through the top list. No, 6 is not there in both. 12, no. 18, nope. 24, nope. 30, yes. So 30 seems to be in both the list. Then move ahead. 36, no. 42, no. 48, no. 54, no. 60, yes. And then there'll be more multiples because this keeps on going forever, right? Say, yeah. So you can see that this list will keep on going and going. So the idea is then, so we have common multiples. So among these common multiples, you can see that 30 is the least common multiple. Least means what? It's a common multiple, but the smallest one. And these numbers are useful. So we'll see later on how does greatest common divisor and least common multiples are useful for us. So what is a common multiple? So common multiples are 30, 60, and so on. And the least common multiple is what in this case? The least common multiple of 6 and 15 is, let's see. So what is the least common multiple? So the least common multiple seems to be 30, right? So least common multiple is 30. And then there is a short form to write down the least common multiple. Again, symbolism is important. Short form helps us to write. So least common multiple of 6 and 15 equals to 30. Then the question is, can I write down the least common multiple easily of some number? Again, tree diagram will come to rescue. So let's see, how do we write down the least common multiple? Okay, so again, let's draw the tree diagram. So question goal is to find least common multiple of say 6 and 15 using tree prime factorization, right? Yeah. So how would we do this? So again, you do the same thing. So you'd say 6 is same as, write down the tree, 2 times 3. Do we need to go further? No, because 2 is prime, 3 is prime. Similarly, let's look at 15. So 15 is same as 3 and 3 times 5. And again, can they go any further down splitting? Can the splitting happen? No, because these are already primes, right? You can check. There's no factor of 3 other than 3 in itself. There's no factor of 5 other than 5 itself. So what you do in least common multiple is, so first of all, you write down 6 is 2 times 3. And then you have 15 is 3 times 5. Now, first of all, what you do is you see what is common in both of them, like you did in terms of greatest common factor, right? So you say 3, 3. Is there anything else in common? No. So now, so least common multiple, LCM, of 6 and 15 is the following. So what you do is you basically start writing one of them. So 2 times 3. So I'll write this as it is. And then I come down to the bottom list and I see, is 3 circled in the bottom list? If it is, then I will not write it. So the idea is to write the circled one exactly once. So 2 times 3 times what? 5. So you write down all the other factors. So you see 2 times 3 is 6, 6 times 5 is 30. So you see, this is not a coincidence. This is how you compute the least common multiple. All right, so let's do one more problem on how to find out least common multiple of, say, again, exercise. Find least common multiple of, say, take some nice big numbers. Let's take, say, 20 and what, 90, I suppose. Okay, so first of all, let's write down the prime factorization. So write down, so step 1, write prime factorization. So how do you do that? You basically go first 20 and then you split it like this, right? So again, as I said, there could be many ways of doing it. One way is to think about 20 is 2 times 10. So 2 is prime, so I'll stop that leaf there. But what about 10 here? 10 is same as 2 times 5. So in this case, I get 20 is 2 times 2 times 5, right? You can verify too, right? 2 times 2 is 4, 4 times 5 is 20. Okay, good. Now let's look at the 90. So 90 is same as, again, I want to do factorization. How do you want to do it? It doesn't matter. So let's say I can write it as 9 times 10. What is 9? 9 is 3 times 3. And 10 is 2 times 5. And these are all primes, right? So I have 90 equals to 3 times 3 times 2 times 5. Okay. So now what is common? I'm going to circle, okay, but exactly once. So 2, if it repeats here, so 2 and this 2. Then this 2 is no, there's no repetition. Then 5, yes, so 5 is repeated. So what I'm going to do is I'm going to write down everything again. So least common multiple of 20 and 90 is going to be, write down 2 times 2 times. So if I write down the first one as it is, so 2 times 2 times 5. And now what is circle in the bottom list? You don't write down. So you have 3 is not circled. You have 3 not circled, but rest everything is circled, right? So what do we get out of this? So we get 2 times 2 is 4, 4 times 5 is 20, 20 times 3 times 3 is, so 20 times 9 is 180. So this is the least common multiple of both of them. Okay. So with this, we have finished section 1.3, and you should be able to finish off the quiz. Thank you.